So now we're going to talk about how to recognize a conic section from the equation, the eccentricity, and looking at solving systems that involve nonlinear equations. So first of all, how to recognize a conic section. A parabola has either an x squared or a y squared term, but not both. So if you only see one squared term, it's going to be a parabola. Circle has both x squared and y squared, and they're the exact same coefficient in front of the x squared and y squared. So that would be how we recognize a circle from the equation. An ellipse has both an x squared and both a y squared, but they are not the same coefficients. A and C are not the same, but they are the same sign. They're either both positive or both negative. That would make it an ellipse. And then a hyperbola, we have both an x squared and y squared, but they're of opposite signs. So that's what we're looking for a hyperbola. So let's look at these equations really quickly. Notice that to get the y squared and the x squared on the same side, I'd have to subtract this over and the y squared would become negative. So we suspect that's a hyperbola. Here, x squared and y squared are on the same side and they're both positive. So we suspect that would be a circle because they're both the same coefficient. Now the x squared and y squared are on the same side, but they're of different values. So we suspect this is going to be an ellipse. X squared, but no y squared. So we suspect this is going to be a parabola. Y squared and x squared, same side, but they're different signs. So we expect this is going to be a hyperbola. Now notice with each of those I said we suspect or we expect it's going to be. Why did I phrase it that way? Because it may not be if it's a degenerate conic section. In other words, if the equation doesn't actually work out. So to check, we have to actually work out the equation. So we're going to do that for each one of these. So if I move that x squared, the 5 to the other side, and then divide to get a 1 there, we end up with a hyperbola much as we suspected. And there's our graph, and there's our information about that hyperbola. If I go ahead and move the if I get this into the standard form, I do so by completing the square. So if I complete the square on this, then notice that I get a 0 on the other side. A circle with a radius of 0 is not a circle. It's just a point. So this is an example where it's not the conic we suspected. We suspected a circle, but the radius doesn't allow it to be. Here, I'm going to go ahead and do the same thing, complete the square on both of these terms. So I got to factor the 4 out of those terms first and factor the 9 out of those terms first, then complete the square on each. Go ahead, get it equal to 1. This is the perfect form for an ellipse. So there is our ellipse and the information that goes with it. So here we suspected a parabola. Go ahead and get it in this correct form. We're going to move everything but the 8y to the other side. Factor out the negative and complete the square on the x terms, leaves a 7 on the outside. Get it into the right form, and we see there's a parabola, and there's all our information about it. And then here we're going to move the, we're going to factor out the 4 from the y terms, factor out the negative 9 from the x terms, complete the square on those two, and then go ahead and see if I divide by the negative 36 to get a 1 over here. This is the perfect form for a hyperbola. There's our information about it and what the graph looks like. So we've got our hyperbola going there. Now, the eccentricity for a conic is the ratio of the distance from any point on the curve to the focus divided by the distance from that same point to the directrix. This allows me to define all conic sections in terms of the point, the focus, and the line, the directrix, instead of defining them in terms of the 2 points like we did with the ellipse, just the foci. So the eccentricity is the ratio of those two distances. Well, the distance to the focus is going to be C. The distance to the vertex is going to be A. And so when my center is at the origin, we're just going to have the ratio of that C over A. So for an ellipse, the eccentricity is going to be between 0 and 1. For a hyperbola, it will be bigger than 1. And for a parabola, it will be equal to 1. So if I'm looking here at the eccentricity of this equation, my 16 is the a, so is the a squared, so the a would be a 4. And then go ahead and find the c, a squared minus b squared, square root it. And c over a gives us a 0.66. That's an ellipse, which is exactly what we were expecting given the equation. That's the equation of an ellipse. My eccentricity here, I've got to first divide both sides by 50 to get a 1 on the right. And then my a is the 10, so the a would be square root of 10, because this is the a squared. And then find the c, 10 minus 5, square root of 5. And so square root of 5 over square root of 10 gives me an eccentricity of 0.71. Again, that's matching what we're expecting for an ellipse. The closer it is to 0, the more like a circle it is. The closer to 1 it is, the more stretched out the ellipse is. And then similarly for a hyperbola, the closer it is to 1, the more narrow around the axis it is, whichever transverse axis it is. And the bigger it is, the flatter the hyperbola is. All right, so I want the eccentricity of this hyperbola. So my a squared is a 9, and so a would be a 3. Find the c by adding the a and the b together, square rooting it. And then c over a would be square root of 13 over 3, so 1.2. So this one's going to be fairly close to the transverse axis, 1.2 for the eccentricity. All right, now I want to find an equation for each conic with the center at the origin and the given eccentricity. So here, if my focus is at 3, 0 and my eccentricity is 2, well, that's bigger than 1, so I immediately know it's a hyperbola. So we're going to use this information to get the equation. This eccentricity is between 0 and 1, so I immediately know it's an ellipse. So we're going to use this information to get the equation. So let's start with A. I know it's a hyperbola, and the distance from the center to the focus is the c, so c is 3. So plugging into my eccentricity equation, the eccentricity is 2, the c is 3. Solve for a, we get a is 3 halves. Use that to find b, plug in the c, plug in the a, we get b squared is 27 over 4. So that makes our equation x squared over the a squared minus y squared over the b squared equals 1. Or go ahead and simplify, there's our equation of the hyperbola for part A. Now the second one we said was an ellipse because the eccentricity was less than 1. And the vertex at 0, -8 is the a value because our distance from the center to that vertex from 0, 0 to 0, 8 would be 8. So again, plugging in, this time the eccentricity is a half. The a is 8. We can solve for c. We get c is 4. Use that to find b, given our equation b squared equals a squared minus c squared. And so plug in, there's our equation of the ellipse. Okay, so let's look at an example of an application of the conic. So suppose that we know that Mars travels in an ellipse and its closest point to the sun is 128.5. The sun is at the focus of the ellipse. Then notice this distance is a minus c, that's my 128.5. So 128.5 is this value here, a minus c. We want to find the furthest it is from the sun, the farthest it is from the sun. That would be this distance a plus c, right? Because from 0 out to here is a, 0 to the center to the vertex is a, and then plus this distance c. All right, so if I know a minus c is 128.5, then that tells me c would be a minus 128.5, just solving this equation for c. So if I'm given the eccentricity, I can plug in the eccentricity is 0.0935. C can be replaced with a minus 128.5 over a. Multiply this to the other side. And then I would subtract this over here and get negative whatever that subtraction is. And then divide off the negative, we get a is 141.8. Okay, so our c then is 141.8 minus 128.5, I'm just plugging directly into this equation right here. We get 13.3. So A plus C would be the A value, plus the C we just found, we get 155.1. So our max distance of Mars from the sun is 155.1 million miles. Now, we can also solve nonlinear equations. If I have this system of equations and I want to know where they equal, where the system is solved, that's looking at the x and y values that satisfy both equations at the same time. So what I can do is I can add these two equations together, and that'll knock out the y squared term. So adding these together, I would get 3x squared plus 0y squared equals 12. So divide by 3, and we get x squared is 4, so x is plus or minus 2. Now, take this x value and plug it into either equation to solve for y. So if I plug into the, I think that's the first equation, I get y is 0. And plugging in the negative 2, we get y is 0. So there are two solutions. The point 2, x is 2, y is 0, and the point where x is negative 2, y is 0. Now, what that is graphing, if we graph the first equation and graph the second equation, we're looking at the intersection of these two figures. Where do they touch each other? And it's only here and here. All right, let's solve this system. So again, we can do elimination. If I subtract the second equation from the first, I'll knock out everything but this middle term. So x squared minus x squared is 0x squared. 3 minus negative 1 would be a positive 4xy. Y squared minus y squared is 0. 22 minus 6 is 16. Divide by 4, and we get y would be 4 divided by x. Now, we can substitute that into either equation. So substitute it into this equation. We're replacing all the y's with 4 over x. So I would have, after I do a little bit of math here, right, these x's would cancel off, and I'd have x squared minus 4 plus 16 over x squared when I square this term equals 6. So I can multiply through by x squared and get x to the 4th minus 4x squared plus 16 equals 6x squared, right? Because when I multiply by x squared times each one of these on both sides, distributing here to the x to the 4th, distribute here to this, and when I distribute here, it cancels with the denominator and leaves the 16. Now move this to the other side to gather like terms, we get negative 10x squared, and now we can factor. This factors into x squared minus 2 times x squared minus 8, so that would be x squared minus 2 equals 0, x equals plus or minus the square root of 2. X squared minus 8 equals 0, x equals plus or minus the square root of 8, or simplifying the square root of 8, it simplifies to 2 root 2. Now, once I know these 4 different x's, right, because we have 4 different x values there, substitute them into either equation to get the y value, and we get 4 separate points where these intersect. Now, I want to find the solution to this system of equations. Notice if this were an equal sign, this would be an ellipse. So it's less than, that's inside the ellipse. This is a hyperbola, it's greater than, so it's outside the hyperbola. So if I graph the ellipse and graph the hyperbola, and I shade inside the ellipse but outside the hyperbola, all of the dots in this shaded section satisfy that equation, or satisfy that system of inequalities. All right, guys, I'll talk to you in the next video.